Okay, for this video, we'll be going through practical electricity tutorial. Okay, so question 1, it shows a 3-pin plug. So this is one of the safety features. This is a water heater of a power rating of 3 kilowatts. Okay, so on figure 1.1 indicate where's the live, neutral and earth wire. So this is simple. I think most of you got it correct. The earth is always at the topmost, and also take note of the color, which is yellow and green. Live is brown. You'll see that the fuse is always attached to the live, and therefore this part will be the neutral wire. Okay, so this is the diagram. Now, what is meant by a live wire is a wire that connects the high potential of a power supply to the electrical appliance. So you can actually refer for the what is live wire in your notes. And what is meant by neutral wire, the wire is at zero potential. Some of you miss out this part of the answers, and it provides a return path from the electrical appliances to the power supply to complete the circuit. Now, what is meant by earth wire? It is a low resistance wire that connects the metal casing of the electrical appliances to earth. This is what you need to memorize. Now, what's the purpose of the fuse in the plug? They protect the electrical appliances from excessive current. Okay, so that is the purpose, and the explanation comes here. When the current exceeds the fuse rating of 13 ampere, okay, when there's an electrical fault, okay, then the fuse will melt and you'll create an open circuit, so the current stops flowing. Okay, and why is the fuse connected to that particular wire, to the live wire in actual? The fuse should always be connected to the live wire, so that when the fuse melts during an electrical fault, this part is the part that a lot of you are not writing. The electrical appliances will be isolated from the high voltage supply. Okay, so this is the reason why switch, circuit breaker and fuse, why are they all connected to the live wire? Okay, so basically during an electrical fault, they will work and then it will disconnect the appliances from the dangerous high voltage, because live wire is physically connected to the high voltage. Now, explain why earthing is essential. So if there's an electrical fault that results in the live wire touching the metal casing, so this will result in the metal casing becoming live, which is dangerous. So the current will actually flow to the ground through the earth wire, as earth wire has very low resistance. Okay, so this prevents a person touching the metal casing from getting an electric shock. And also the fuse will melt, right? Will melt, because we don't want the current to keep flowing into the earth wire into the ground. That will result in a lot of energy wastage. So the fuse will actually melt to create an open circuit, and this is to inform the user that there's something wrong with the electrical appliances, probably an electrical fault. And the fuse will actually disconnect the electrical appliances from the dangerous high voltage, so that when a person comes in to repair, he touches the appliances with the metal casing, he will not suffer any harm. Okay, so if a technician wants to measure the voltage of the power supply, between which wires should the voltmeter be connected, live and neutral? Ground is never in the picture. Ground will usually not have current flowing through, but live and neutral wire will have current flowing through. Okay, so question 2, it shows a 240 volts 20 watts lamp. So this is for the lamp A. 110 volt 30 watts lamp for lamp B, connected in series to 110 volt main supply. So the main supply is only 110 volts, which is good for this B, but it is not enough for A. So we will expect the brightness of the light bulb A to be less than 20 ohms, and because now they are connected in series, their potential difference is the sum, so we will also not get 110 volts across B, so it will be less than 30 watts as well. Okay, now calculate the resistance of each lamp. So regardless of what circuit it is being connected to, the resistance of each lamp by right shouldn't change if, let's say, the temperature and the surrounding doesn't change. So the resistance is based on R equals to rho L over A. Okay, but with the power rating, we have this is V, this is P. okay, and we have this formula P equals to V squared over R. So we can straight away calculate the resistance, okay, to be 2880 and 403 ohms, okay. Now calculate the current drawn from the main supply. So because now we know their effective resistance in series, the voltage is actually 110, so we can actually get the current that flows. Okay, suggest a suitable fuse rating. Now this one, when I check internet, they say usually it must be 20% higher than the actual current that's flowing. Okay, so in O level, they will also maybe throw in a few numbers for you to choose, because then there'll be some ambiguity. Okay, so some of you wrote 0.5, or sorry, 0.05 ampere. This is okay, but 1 ampere is a bit too high because the current is 0.0335 ampere. Okay, we can discuss about this. Okay, but usually what I see in O level is that they will actually give you some options. Then the options are quite distinct so that you are able to make a right choice. Basically, the fuse that you need to use, it should be slightly higher than the working current. Okay, calculate the power developed across each lamp, because they don't have the V. Okay, the V across A is not 240 volts, the V across B is not 110 volts. So I need to use the current, and we actually have this P. We actually have the P equals to I square R formula to help us, because the current flowing through both of them are the same, and we have calculated the current flowing through each lamp from part B. So we can actually do our calculation here, and you'll see that for lamp A, like what we see just now, it will be less than 20 ohm, right? Because it doesn't get the full 240 volts across it. This 20 watts of power will only happen if the potential difference across A is 240. But because now they are connected in series, plus the main supply is not 240, so it will definitely not get 20 watts. Similarly for B, so even though the main supply is 110, but because we have two light bulb in series, so it will also not be 110, so it's actually 0.452 watts. Okay, so which is quite lower than what was expected. Now, which lamp is brighter? So lamp A. Okay, so the brightness actually depends on the power. Now, complete the following table when the circuit is working normally. This is important. So current will flow in live and neutral, okay? But if there's no electrical fault, there should be no current flowing in the earth wire. So for live wire, it is 110 based on the question. Neutral is 0, so it's safe to touch, okay? But not that I suggest you to go and touch it, but it's safer than live. Earth is definitely safe, 0 volts. Now, in this circuit, one of the lamp fails, the other lamp will not operate as well. So to solve this problem, suggest that the lamp should be connected in parallel. Okay, state 2 advantage, so both lamps will be brighter than when they are in series, right? So if they are, let's say, connected in parallel, so lamp A and lamp B, okay, B is 110 volts, the power rating of 30 watts. A is 240 volts, 20 watts. Okay. Yes. So which one will actually achieve the full brightness is actually B, because it actually has 110 volts across it. Okay. Whereas for A, it will not be as bright as 20 watts. Okay, because it needs 240 volts to be across it. Okay. And if one lamp fails, the other can still operate. Okay, the other lamp will not operate as well. So actually, they actually tell us about this solution already in the question. So yeah, so I think this one should be only one advantage. Okay, now one of the disadvantage of this is that there will be higher power consumption. There will be more current drawn from the mains. But actually, to me, this question is that there's also no disadvantage, because basically the purpose of the lamp is to light up, and I got to pay for whatever I use. Okay, so yeah, anyway. Okay, let's go to question 3. Table 3.1 and 3.2 show the electricity tariff charged by Singapore Powers and the power rating. Okay, so we take note that every kWh it is charged in 20.52 cents. Okay, 20.52 cents. That means 1 kWh, and 1 kWh is actually energy, because it's power times time, right? Although it's not in our SI unit. So 1 kWh is 20.52 cents. So we have a few appliances. Aircon is 750 watts. Clothes dryer is 5000. Computer is 200. Fan is 115. So you have to be very careful. You have to read the question. Calculate the amount of energy consumed by the computer. So we need to zoom in on computer. Is 200, and it's 200 watts after operating for 30 hours in kWh. Okay, so they want us to calculate in kWh. kWh, like what I say, is power times time, but it has to be in a certain format. So you need to convert it to 0.2 kW and make sure the time is in hours. So it's really in hours. So I'll get 6.00 kWh. So you leave it in 6 kWh. I will mark this and I'll put a 3 SF. Okay, so take note of the SF. Now calculate the amount of energy that can be saved when a portable fan is used for 150 hours instead of an air conditioner. So for the fan, we notice that it's 115 watts, so we also need to convert it into kW, and the hours is 150 versus air condition is 750 watts. So again, convert it to kW and same timing. So we have a fan using 17.25 kWh, that is the amount of energy. For aircon is 112.5. So what's the difference in energy multiplied by the amount of money, the cost of 1 kWh, and we'll get 1955 cents or 19.55. When you're calculating in terms of money, right, or cents, right, you don't actually need to follow your SF rule. Whatever it is, you just show it, okay, but not to like 20 SF, okay? Yeah. Explain why it's dangerous to handle electrical appliances with wet hand. Resistance of the skin reduces when it is wet. Okay, some of you put there that water is a conductor of electricity. Please don't write this. We can actually tweak our answers to say that when skin is wet, the resistance of the body is reduced. Okay, so this is a better way of saying rather than saying that water is a conductor of electricity. Okay, so therefore when the resistance reduces, it will increase the current flowing through the body if there's any electrocution. Therefore it increases the severity of the electric shock. Okay, so this is the answer for your practical electricity.